Patty, and over to you straight away.
Okay, thanks a lot for the opportunity to speak. This is on a model that we actually worked on for a while. We at first were involved rather closely with several people here, Chuck Gartland, Carmen Caldera, and Dan, and myself, and a couple of other people, chemical physicists, Tony Yockley and Chris Bailey at the Liquid Crystal Institute, and a numerical analyst, Jay Shen at Purdue. And we did some modeling with them to try to understand a radial symmetric bentcore fiber that they were able to form in the lab, and it was quite stable. And they were anxious to have some more evidence, not just the experimental evidence, but showing through modeling that this might be stable against other non-radially symmetric fibers. So this is where it came from, and then later on we did a little more work, and this is about that. So let me start then. So as I said, it follows the experiments on B7 symmetric liquid crystals by Chris Bailey and Tony Yockley, and Chuck Gartland was also involved in the modeling. And these materials form fibers of very high slenderness ratios on the order of 1,000, whereas Newtonian fluids have length over diameter, very comparable. And there's a high level of molecular self-organization that causes the formation of these fibers. That's a picture of what they looked like in the lab as they were forming them. And experiments suggested that fibers consisted of cylindrically symmetric layers forming around a non-symmetric core, and that they could have circular cross-sections, modulations, be helical, have telephone cord structure, etc. And there's a lot of work in Colorado on some of those other phases. And some of this is theirs. They see, they freeze the fiber and look at things that way. And the symmetric layer structure, here's sort of a schematic of what it looks like. There's some non-symmetric core, and then these bananas form around it in layers. It is a symmetric C kind of material that they see. And the molecular structure is shown here. I don't know very much about that. And mathematically or otherwise, one models these by a director field N and a polarization vector P. We take them both to be unit vectors. And the polarization that comes with these is assumed to be a constant P naught times this unit vector P. And so the schematic is that this is how you imagine these banana fibers, and they have polarization. And this molecular shape is part of the picture for self-organization, elastic or molecular packing, and electrical repulsion were things that they thought were major effects and reasons for the formation of these. And one gets a kind of a splay or polar divergence, and a layer bending, which is something, well, for us was rather unusual to try to formulate a symmetric model in which you would have layer bending. Most of the models are for boxes or something that's layered in a, vertically, but not bending like this. So first part here I want to talk about is the free energy model. And this is based on the one-dimensional model that, Bailey, Yockley, and Gartland started with and analyzed. And here, again, as I said, it's described by these unit vector fields, n and p. We assume that the polarization field is a fixed multiple of that, and that n is orthogonal to p. And there are a lot of phases that this forms, and they have different properties. The symmetric AP, here I'm thinking of this dark part as the layer, the layers are forming in between. Symmetric AP has n parallel to the unit normal here. And symmetric CP has a tilt angle theta with k, which is the unit normal, but p is perpendicular to n, but also parallel to k cross n. So that's another phase. Whereas here, the p is not parallel to k cross n. We do have a tilt angle theta, and that's the B7, which they were particularly interested in. And then the leaning phase here has n and k and p all in the same plane. That's the leaning phase. So in general, we can describe the n and p by angles theta, alpha, and phi. And that's what the model that Chuck was involved in did. The theta is the, we take to be between 0 and pi over 2. It's a tilt angle of n. We are often thinking of those in symmetric materials. So it's here, nu is like the layer normal. This is like the layer. We can think of the layer as here, tangent to t. And so theta is the tilt angle with the layer normal. And then we have since p is orthogonal to n, p can locate on a circle here around n. And so we have an angle alpha. They often call it the molecular tilt because n and p form a plane. And this is the angle from nu cross n, the position of nu cross n, to the position of p on this circle that is on the plane perpendicular to n. So that's alpha. And then I think, that's alpha. And then phi is the azimuthal angle of n on this tilt cone. Given that n tilts theta, it could be anywhere on this cone about n. And that's, and the place where it is on that cone, the azimuthal angle that it forms, let's say its projection forms with t, that is phi. So those are the variables that are used a lot. And what is found in the lab is that it takes a lot of energy to vary the layer thickness. And if you change the tilt angle theta or the molecular plane angle alpha, that will change the layer thickness. But this azimuthal angle phi, where n is on that tilt angle, does not. And so theta and alpha, they think of as stiff variables, whereas phi is soft. It's more free to move around. And here's one of the pictures from Bailey, Gartland, and Yockley's paper. I think that's Phys Rev E. And so they found B7 forms single stable cylindrical layers with radii in a narrow size range. They proposed a free energy within that framework, and they assumed constant fields for n, p, and that they had circular symmetric layers. But here there were unknowns of the radius of the core and the radius of the outside, because these were pulled in air. And they fixed a physically reasonable value of the core, R naught, and then they computed an R that would form a critical radius at which the circularly symmetric fiber would be stable with respect to other values of R in their computation of the energy. And so they took theta and alpha fixed but arbitrary in this region. Constant azimuthal angle phi equals 0 on the tilt cone with angle theta about ER. And they assumed a physically realistic radius. They found this critical radius. And what we wanted to do, and what Bailey and Yockley were very interested in us to do, is to see if we could together come up with a model that would allow non-circularly symmetric layers, and would it be stable against perturbations that were not radial? Because I guess not everyone believed that these fibers were stable. And I think that especially Clark's group, they often had, corkscrew type things, and there was some, I think the discussion that I remember was that they were working in different temperatures, and they were freezing when they took their pictures. They were I don't remember the term, but they were freezing these and then getting their pictures. Is that about right?
Yeah, I think they were freeze fractured.
Yeah, freeze fracture is the term.
And they, like you had a picture earlier, they appeared to have kind of an undulation to the
Yeah,
layering.
yes,
So
they get these telephone cord type things and many other things. But they do work at where they're taking their pictures at a different temperature. And temperature was supposed to be a very big factor here. They pulled these in the air. So that was one of the first things. We had a focus research group on this, the 7 of us, and this was one of our first projects, was to go in and try, or at least Dan and I and Yockley and Bailey and Carmel also worked. You worked on a different kind of bent core, right? More ribbon shape. So here we want to look at non-circular cross sections and non-constant fields, and we formulate a free energy, and we need an elastic energy. We put in a Chen-Lubensky type symmetric energy, and also they had formulated a packing type of energy for the bent core, which is we put in as part of this. And then we have many other terms, a surface term, polarization, distortion, electric repulsion type of term, core energy, Frank energy. We assume that our region is what we call a generalized annulus, a region between some any simply connected smooth domain omega and another one omega naught with smooth boundaries. And so omega is the region in between those two boundaries. So let me just go through some of these terms. We worked hard to make up this model. And for the surface energy, Lavrentovich has a model that he uses for that, which is having two constants that are affecting the surface energy on the outer and the inner surfaces. And here that would be of this type, and those were two positive constants. Then the dipolar divergence distortions, that's the F sub p. The field tends to splay, and it has elastic and electrostatic origins, has a polarization which can be negative, and the term that was used there was an F sub p, which is a constant, Cp times the divergence of p, which you can integrate out as as a boundary term. And this does tend to be negative, and you can imagine that this likes to splay. Okay, the elastic term. This is what was used in their work. So we took a similar kind of term. And so here phi is on sigma, 0 boundary values. Sigma is the region inside the outer gamma 1, and it satisfies this elliptic equation. Divergence of p times the characteristic function of omega. So this is harmonic outside of omega, but otherwise Laplacian of phi is this. And the electric term is then length of E squared, a certain multiple, minus P dot E. And that turns out to be this multiple of grad, when you integrate it, it turns out to be this multiple of grad phi squared plus P dot grad phi after integrating by parts. And so the electric term we define as this then. It integrates out to be another multiple, a different one from what you started out with of grad phi squared.
The electric potential is 0 on the boundary?
Yes, the phi is 0 on the boundary, but yeah.
They said that there was ionic screening.
Yes, they
was there.
they mentioned some kind of screening that they assumed certain things balanced out.
Okay.
That's all I can say.
So there's no field outside, no junk, no charge density?
Well, they were saying that certain charges collected and they would balance out. I don't know, whether there would be other better choices, but this is the one that they had made in their model. Okay, let's see. So these 3 terms that I just talked about, they dominate in the energy. And then these other 3 terms, let me talk about those. So this is the elastic core and the symmetric part. Their energy contribution is small, but they have a lot to do with second variation. So the core energy the core is assumed to be isotropic, and we take it as in the end, it's really a free boundary. You can't really prescribe the core. This thing forms these layers until it's not energetically favorable. And so the core energy is B times just integral of B over we call it the generalized annulus, omega naught. And let's see, here is B. It's this is the pneumatic symmetric critical temperature. It's a constant plus another constant times this difference. So as temperature increases, this B decreases. Frank energy density, we just take to be one constant approximation. And finally, the symmetric energy. And we take, this is our symmetric layer density. It's a combination really of 2 things. We throw in the packing term with this. So the Chen-Lubensky energy density, we use a version of that for one of the group of terms. And here's what it looks like. And you can think of multiplying and dividing by q squared here if you like. But we write this, this is a small term, so we write it this way. Q is large. The reciprocal of Q is related to the size that the bulk would like to have in their symmetric layering. And this Q large, because those are on the order of 5 nanometers, those layers. And here we also take Q large so that this elastic constant and both of them are small, but they are there. So there is some penalty for bending, but here are the coefficients, and this really doesn't affect energy minimization. Let's see. We're taking length of psi to be 1, so that's just an added constant. To complete the square, I'll show you what this looks like later on. And as usual in the Chen-Lubensky energy, well, here we assume that C perk over 2A perk is between 0 and 1. And also, usually in Chen-Lubensky, you take e to the I q, you take e to the I omega. This is just a change of variables to normalize rather than wanting when we have layers that are very much like q in length, in thickness, then that'll be like omega being 1. It's a normalization or change of variables. So as I mentioned, this is Q is 2 pi over d naught. D naught is the preferred layer thickness. It's very small. And in the Chen-Lubensky energy, these derivatives are covariant. It's in here, grad minus some multiple of Q psi times n. That's what they are also in superconductivity. And then the other term, d parallel. D parallel has this term in it, and d perk is the difference. So that's the d perk and the d parallel. And this was what Chen and Lubensky and also Ren and Lubensky developed as models for symmetric. And here we define sine squared of theta naught equals this. That should be C perk over 2A perk, this number that's between 0 and 1. So that's all part of the Chen-Lubensky setup. And you can see how it favors a tilt angle. Here I just said we are setting this number to be sine squared theta naught. And the reason you can see here, when psi is e to the iq omega, so when you apply that energy to e to the iq omega, then you end up getting this, and these are all non-negative terms, and you can see that grad parallel omega, which is grad omega dot n, wants to be like cosine of theta naught, so that's the cosine of the tilt angle. And similarly, the perk of omega, and the sum of these two give you the gradient. This Chen-Lubensky energy really beautifully prefers that, prefers or gives some preference to a bulk tilt angle energetically. And again, when Q is much bigger than 1, then you can see that because of these two terms, should be small because they're multiplied by Q squared, then grad omega in length is close to 1, and the tilt angle is very close to cosine of theta for that. And so those are the components, one big piece of the symmetric, and this probably should be its own term, but I think 6 is enough. So we've lumped this in with the symmetric, and this is the chiral packing energy density. It looks like grad omega cross n dot p squared, grad omega dot n squared, minus a number chi naught squared times grad omega to the 4th. And what that favors when you divide through by the right power grad omega to the 4th and pull it out, is that these terms, this term will favor cosine of alpha naught, and this we know already favors cosine of theta naught. Oh, and this one is cosine alpha naught times, let's see, cosine theta naught, and those are squared. And so this one has a preference for a certain alpha, a molecular tilt to the N and P plane. has a preference for a certain tilt, that one. And, well, grad omega cross n dot p in length is sine of alpha cosine of theta. So in that way, you know, again, if that's multiplied by something large, and so you're going to have a strong preference for that angle, tilt angle, and the molecular tilt to the banana. And so we define the sum of those two densities as what we call the symmetric term. And so now we look at energy minimizers and a free boundary problem, because one could estimate the core by some physically realistic number, but I guess mathematically it's going to be some kind of free boundary that forms in competition with this energy. So we look at the energy, which does have that Q in it because of the covariant derivative was grad minus I Q cosine theta naught. And so we are then going to look at existence of energy minimizers and try to analyze a free boundary problem, see if there are radial solutions, see what their nature is. Are they constant, which is what they observed in the lab, that these were radially symmetric, and are they stable against non-radial perturbations and non-radial configurations. So here these are defined, the energy is defined on omegas, which have second derivatives in L2. They're going to be 0 on gamma 1. They're going to be a negative constant on gamma naught, and you can think of as inside the core. That's what you would want for something that could act as a layering, something that promotes layering or describes layering. And the N and P are unit vectors with first derivatives in L2, and they're in L2, and they're orthogonal. And here layer thickness is small, and so we think about if we can get energy minimizers letting Q go to infinity. And in general, if gamma 1 and gamma naught weren't related, this energy would not be bounded above, but if it is finite, we capture a singular limit. So we look at this energy, and we are able to show that there's at least one minimizer for each Q. And that's a fairly standard argument, because the energy has good convexity properties in the gradient. And now we set A infinity to model that, what sort of a reduced problem, what would we get by letting Q go to infinity, or do we get anything? And so A infinity is going to be, you know, if you could let Q go to infinity, it would fix a tilt angle in that, you know, this is cosine, well, it would fix here, grad perc squared is sine squared theta, and so cosine squared would be grad parallel of omega in length. So it kind of would fix a tilt, it would fix a tilt angle in A infinity. And also we would say that this packing term should be the one that is equal to what is preferred in the bulk. So that's we call admissible set A infinity. And we define the reduced energy, which is what would be left when you have this. This fixes the theta naught and the alpha, and well, I guess it fixes up to four values, alpha. And so the energy then looks like this. What's happened is that the symmetric term has reduced to this. And what we find is that if these, the infimum of these F sub q energies, if those minimizers would have bounded energies as q goes to plus infinity, and let's say greater than or equal to 1, then you can find that there is something in this space with fixed tilt angle and molecular tilt. And there would be a minimizer in there, and it would be the limit as q goes to infinity of these. But that is a big assumption, you know, that even that, that you have this A infinity, that it's not an empty set. And
Can I look at that again? Is the phi, there's no, so all that survives in the symmectic energy is basically the divergence of the layer normal. That's
no,
the curve.
we're just
That's
saying
not the
this
curve.
is going to be our admissible set. So that phi is completely free out of this.
Okay,
Or
I was
A
just trying to see
infinity.
where in the F infinity is your limit free
F
energy.
infinity is going to be our limit if it exists. Uh-huh.
Okay.
In other words, this thing may not be bounded for some domains, and A infinity, you may not even have things in there. Okay?
But are phi-related distortions penalized
Phi,
in some way?
Well, you know, they're part of, you know, they're part of the relation between, I mean, they're the soft variable. So they're, you know, we have gradients that are, you know, you can't vary too much. Grad p squared is was one of the terms, nu times grad p squared, and so, you know, there is some penalty on them through that also.
The variable phi would presumably have its softness broken by the curvature, wouldn't it? Because not all directions in the perpendicular to the layer normal are equivalent in a cylindrical geometry.
That's right, that's right. So they are affected by all those things.
Yeah.
And this, you know, is a simpler symmectic term, but it's still there. There's still this symmectic energy density that is part of this. And so what we find is that if this were bounded above, we have a minimizer to this limiting problem. And then there was, somewhere in those terms, there was a coefficient, nu times length of grad p squared. It was part of the Frank energy, it should have been. And that nu often, as far as I can tell, well, I think that, is this true that physicists don't like to penalize the gradient of p too much? But I don't know. Anybody have a comment on that? So anyway, I think that Chuck, you guys didn't penalize that at all. What?
Sorry.
Pardon?
Similar theories do need, I mean, if you look at the equivalent pneumatic theory for
Right.
that needs a grad p squared.
Right, So I think, anyway, it seemed that the desire was to have nu be small. And so that would mean that grad p could, it's penalized, but it could vary, you know, more freely than n. And that would also be part of this phi, the freedom of phi. So suppose that this admissible set A infinity, where we're really fixing the tilt angle, and we're saying that the alphas have to stay in a set of 4 values, then there is a state in here that minimizes this energy, A infinity, which is, which I'm going to call F infinity 0 over A infinity, which is the limit as that coefficient, viscosity coefficient in front of here goes to 0. So if A infinity were not empty, then we would be able to reduce the energy even more and have this as our reduced problem, F infinity naught, where this coefficient would have the limit of 0. And part of why we can get this is the fact that in A infinity, we do have alpha and theta naught taking only 4 possibilities, but we also have that cosine of alpha of x as you go around the material and sine of alpha of x are in W1 too, because you know, we did have a small multiple of grad p squared, and then that means that they would have to be constant. So it's easy to get a subsequence that converges because they are unit vector fields, converges in L2. And we show that for minimizers, here we call it this omega bar, n bar, p bar. For minimizers, when they do exist, that they would have to be of the form negative distance between x and gamma 1. So this is a strong condition on the domain. And gamma naught would be a t-level set of this distance. And in that way, a core would be formed. That's the way the core would be formed. And here, when you have this kind of domain, I am looking at something, or thinking about something that is a small perturbation of a circle, and it can be described by these polar coordinates, and where the normal comes in and can be part of the coordinate. So this is something we call a ruled domain. So in a ruled domain, omega bar has to be like this, negative distance. So it's a very stiff problem, but still phi is allowed to vary. So in terms of this frame, because here we would have coordinates, the coordinates of this angle, the polar coordinate, and then minus t nu would be the other coordinate. And so along with those coordinates, we would have a tangent direction, and in terms of that frame, then we have the tangent vector we can think of them as layers, or really it's just this coordinate system that ends up being available, and nu, the outward normal to the distance, level curves of the distance, and then n3 t cross nu. And the polarization, well, first of all, the n1 is fixed because the tilt angle is fixed in A infinity. And so the n1 in terms of nu, t, and ex3 can be described. And you see that just the phi is not fixed. And the polarization, but n1 is fixed. And the polarization p in those coordinates also has its first component fixed. And it's got a variable phi. So 1 degree of freedom for that limiting problem. And so given omega, if A infinity is non-negative, we have these this problem set up, and the free boundary problem is then described with the unknowns gamma 1, t, and phi. And on a standard annulus, we find that any minimizer will have omega of x being length of x minus r. This is for an annulus where r is the outer boundary and r naught is the radius of the core. And phi would have to be constant, taking either pi over 2 or minus pi over 2. And you can see that by looking at the energy. It splits up into several a collection of a sum of terms which are non-negative, several groups that are non-negative, and from that you can read off that that phi will take on these values, and so that would be, but this is if we have a minimizer. We have to have a particular type of domain in order to have this minimization, this A infinity being defined.
Just, sorry, Patty, plus or minus pi over 2, does that mean it's tilting in the direction of the
No,
axis of the
it's one of
cylinder?
those. It's one or the other.
Yeah, but does that mean, I can't remember your origin or your coordinate system, is it tilting in the direction of the cylindrical axis, or is it tilting in the circular
That would
cross-section?
mean that it's, if you look at the normal cross n, that's the 0 point. So pi over 2 from there. Pi over 2 from the normal cross n.
Yeah, I think the question is, how does that relate to the cylindrical geometry? Does it go around the azimuth, towards the azimuth, around the cylinder, or along the cylinder axis?
It tilts.
This phi, it's let's see.
I believe it goes along the
It's-
axis.
Pardon?
I believe it goes along the axis. The phi dot that you're getting, I think it goes along the
There's-
z-axis.
Well, we have n. N cross phi is going this way, and then they are on those two sides.
So yes, so it's along
Yes,
the
so
z-axis.
it's going towards or away. Those are the possible values, towards or away from the edge. And, okay. And here, there's, well, okay, let me continue. So N1 is determined, and we can define this constant. It involves the Frank energy, the A perk, and N1. And we can write then the energy, work out the energy for the radial problem. It turns out to be a function of R, and a function plus a function of R minus D. And you can compute the radius, R naught of the core, and find that when lambda is small, and if this term is non-negative, this one relates to the core and to the polar divergence, then there's no local minimizer for this problem, even among annuli. And if this thing is negative, then we have a unique local minimizing state. So there are certain annuli that are being formed, assuming that these two conditions, which are reasonable for what happens in the lab. And you can analyze what happens as lambda goes to 0. So if this is non-negative and this thing is negative, we do get sort of there's a critical radius and a critical core being picked out by this. And then we want to look at stability. And for that, we investigate the limiting energy, or the reduced problem, as nu goes to 0. And there's some math that I'm skipping here, but this annulus that we've just found with its core, it is admissible in the sense that the A infinity is non-empty. It allows this kind of these minimizers and minimization. And one can show that if you look at a domain where the outer boundary, gamma 1, is close to the polar function in C3, about that origin to the outer boundary of that core that's been picked out, or that fiber that's been picked out with the critical radius, then that will be admissible. So if we've got this cylindrical fiber that is of a critical radius and critical core, we know there's one, that it exists under these conditions that I mentioned. Then if you take a small perturbation of that outer radius, then that will also have a free boundary problem and a description in terms of the distance. Okay, so we call those admissible. Anyway, there is some math that once we're near this one that we've picked out, then there are admissible ruled domains, and they're characterized by their outer formula. Could be some corrugation of the circular boundary of the critical symmetric radial fiber, and they will have an inner core formed, and you can think of that energy or that energy functional as this is the limiting energy as nu goes to 0. It's a function of n, p, which are only functions of phi now and of the distance. That's all that's left to vary. And what we find is that for those admissible regions, in other words, they have an A infinity that's not empty. We can look at those and we see that the critical symmetric radial fiber, that this thing away from that, it varies by epsilon squared, second variation, so it's a critical point among the non-radial fibers that are still close to it. And also that if we look at for stability, there are some conditions. Remember, B was a constant plus some multiple of T naught minus T. So there's a number here, which I could give, but I'm not giving. I mean, it's in terms of theta naught, etc., and the coefficients. If B is less than or equal to this certain number, then we have stability of those fibers. And if B is bigger than this other number, then we will have that the second variation is negative. And this minus B increases as temperature increases. And this kind of matches the phenomenon of Yakli, that they could pull these in a certain range of temperatures, and also we checked some of the constants of the radius, the critical radius, etc., and they matched, they matched, not exactly, but they were in the ballpark, because these things are of sizes like 10 to the negative 9 and that sort of thing, these core radii and radii. So that's what we've done on this problem. And it's interesting that even when you don't force the radial fiber to have phi be constant, it will pick that out in this reduced problem. And also that we can show that once we've got one of those small C3 perturbations, we'll have a free boundary, a level curve of negative the distance, for which that A infinity is non-empty, and therefore you have a minimizer for this problem, and you can compare it with second variation and find that in this range you have stability, and depending on temperature, which is what is known, it could be unstable in other temperatures. Gets too cold, basically. Gets too cold. They're not stable. So that's all I have to say.
Thanks very much. Got some questions?
Yes, when
you do not limit at infinity. Could you interpret it, if you were to interpret the scaling and bring in the dimensions, could it be interpreted in some way as a limit of a thin fiber?
Well,
Or
these-
it's a different limit? Or in other words, how would you get the limit of a thin fiber in this problem?
Well, these fibers are already quite thin because of the Q. And they're already quite thin. I mean, in other words, when you look at these, you can look at these numbers, and they're, do you remember, Dan? I think they're on the
Like
order
10
of
to the
10 to the
minus
-9 or,
10 to the minus 7th is the fibers, and 10 to the minus 9th, I think, is the core.
okay, the core. Yeah, so they
What?
are quite small. These are the critical radii in the critical core.
But you could still get a model that would be an approximation in the case, say that the radius is very, very small, independently of Q. Okay, what I...
Yes, those are two different things, really.
It's
Q
just a
large
different
means small distance, or small, small thickness.
Because in that
Layer
case...
thickness
yeah.
is the zero
Layer
layer
thickness.
thickness.
Yes, yeah,
Layer
but if
thickness
the
is
geometry,
Q.
if the tube is very thin, because in that case, if you were to leave, say, the axis as free, then there could be a configuration with less energy that is actually the telephone cord. But that cannot happen unless you have a very thin, in some way the energy has to scale it, so...
Well, this one picks out the
do you
critical
become-
radius, like it did in their example.
But is there a situation where you
It's
could
small,
actually...
but it's not really a limit as, I mean, it's picking it out from 0 to infinity. It's picking one out.
But the
Because-
cylindrical
yeah.
geometry is assumed, it's not allowed to coil up or anything.
Yeah,
like
that's,
you're worried
but, yeah,
about.
you would be changing one condition.
Yeah, we're assuming a
basically-
fixed cross-section.
Yeah, but if you were to leave the axis free, say that could happen in shape.
Yeah, that could, I mean, and that is, I think that's an interesting question for how these could go unstable, that they may become helical, for
Because
example.
then one way to,
Because that is an assumption here, is that the cross-section, everything is uniform with respect to, another cross-section.
because then at the limit, what you'd be getting is that instead of screening the polarization and the boundary with the charges outside, in a way that the polarization would self-compensate by, following hills.
Yes, yeah, anyway.
think
In
they-
ribbons,
they-
yes, ribbons is clear, but not so much in here, I don't know.
I mean, I think they see in their experiments some helical fibers, but more in like a melt, not in a freestanding.
In the
Yeah.
melt, when it starts to nucleate, it nucleates
Nucleates
within the
the
hot
nucleases.
bath as
Right,
as
right.
Yeah.
it solidifies.
Mhm.
That's why I think, it probably relates to temperature and that, when these do
Yeah,
get into
definitely.
the,
It's a low temperature thing.
yes, and the environment. Yeah.
When you look at how they grow in the melt, this is phenomenal. They not only do like that, they just go around all around the place. It's completely unstable. It's great fun to watch.
Yes,
Makes you want to be an experimentalist.
It's very
Because you're
clear.
baffled by it completely.
yes.
Yes.
Tim?
Could you, when there are two parts to this problem, right? One of which is concerned with what is the structure inside, and the
Mhm.
other of which is concerned with, in some sense, is there some free energy minimum for some particular finite size? Have I got that right?
Yes,
So
and that the
what-
critical
and what we're
radius will
seeing
be
here
picked
is
out
what-
partly by
Right,
that.
so what we're seeing in what you're, I like pictures, you see, and I don't see a picture of my free energy as a function of the thickness. And what I want to know is, what, you see, you're losing your
Oh.
stability.
Well,
You're
that
losing
was,
your stability, you are saying, right? So you have some finite size chord, and then as the temperature increases, all of a sudden it could grow infinitely thick. So the question I want to know is to see a picture of my free energy as a function of thickness. And I
Mhm.
guess the other question I
Yeah,
want to know
this
is,
is that.
in all of these things here,
this is
which
that.
bits of my model can I lose and still retain finite, right? I think that the size of P0 is in some sense key for understanding, which is telling us something about polarization. In some sense, this
Yes,
is
it
key,
is.
and I want
It
to see
is.
a picture of how all of this is working. Right, I want to know when you lose your stability, is there I mean, if you got something that was larger, is there does your stability get lost because a minimum and a maximum combine, or does it get lost because the size actually diverges?
Okay, well, let's, I guess I have something, it wasn't part of this, but the B, that was, you know, constant plus another constant times T naught minus T. And so instability is when this combination, 3Q1 plus 3/4 Q2 plus Q3, is sufficiently small, right? And I think I have something, yeah, I didn't make a slide out of that, but these are those three constants. Those are those three constants, one of which has the P naught squared in it, and the tilt angle, and these elasticity constants are part of it. The chi squared is part of it. The alpha naught is part of it. So it does come in, and it also comes in the formulas for the size, but I didn't write them down.
I just
Here.
can't quite see what is competing with what in order to allow this to grow to a finite thickness, or alternatively grow to an infinite thickness. And when
Well,
you reach
yeah.
the limit of stability, does the size diverge?
But
the
I think, you know, this
Right
is
here.
the form of
That's right
this.
here.
This is it.
It's right
This is
here,
the energy
bottom one.
for, you know, for 0 less than R naught less than R, so that R naught is R minus D. And this is the formula for the radial. This is, and it's very similar to what Yackley, Bailey, and Gartland had, except that here we haven't fixed the core radius, but we have allowed it to be free. And this thing will pick out the, you know, an R bar and a D bar, a distance away from it. So this is it. This is it.
But
And-
the question is, as it loses stability, does R go to infinity?
No, that's
think
not
it's-
it.
It's all finite.
It's just the structure of the director of the field.
There is only one local minimizer here.
That's right. But I guess your question is about what's going bad. What's going bad are the
When you
non-radial
lose, right, you
perturbations.
see, when you lose, right, I mean, what you're saying is to Martin, when he does his experiment, right,
Mhm.
that he changes his parameters slightly, and all of a sudden his fibers, instead of being finite, will in some sense could grow infinitely large. Is that?
Or do something else, we don't know what that is.
Right, so I don't mind that we're not worrying about telephone instabilities, but I do want to know what happens when things go wrong. Right, I want to know whether, you know, whether they're
Well, I guess,
whether the minimizer is an absolute minimizer. Is that what you're saying, or it's just
Yes.
relative?
well, this one is a local minimizer.
It's a local minimizer.
This one is-
So in fact,
but
it
it's
could
the
be
only one.
that it could be that there's some sort of statistical fluctuation that could jump me out of this. And if it grew just a little bit bigger, then it would sort of, you know, this is what happens, for example, in nucleation problems, right? In nucleation
Right,
problems,
well,
if
I think that here, you know, there's so much structure already in the problem from having assumed the circular, you know, that you have just one cross section at which, you know, if you go to another height, it's this,
Well, I don't
the same.
mind that we've got.
and yes,
Longitudinal modulation.
and there is only one state
Yeah, I
for
like
this
that.
particular setup. But the other thing, you know, is that this was a limit. This is an approximate problem, right? Because we took the limit as Q goes to infinity and the limit as
No, it's fine, I'm
Yeah.
not against approximation.
So with the energy at the top there, so I've got an energy there as a function of R. What does that look like as R goes to infinity? The energy? Is it go to a constant?
You know,
Is it? Well, okay.
So this is the radial problem is just very
It
well
blows up like
defined.
R squared.
The radial problem is very well defined. You get a nice, this is a
Yeah.
nice minimum.
here it's r squared, right? At infinity, and like log of r
The
at,
instant, yeah.
going to 0.
The instability
And
is
here
within
it's also,
the
quadratic and
non-radial
log.
perturbation.
Yeah, oh yeah, that's right.
yeah.
That's
So
it.
we could give a picture. I think we did in our paper, but I didn't put a picture in here.
I
Yeah.
think that, Tim, when you mentioned the instabilities, if I don't misrecall, I think one of the papers, or in some of the experiments of Jackley, when reaching a certain thickness, it started developing focal conics all around. It's coming out like fruits.
So where's the signature? Right, oh, sorry, everyone is
Let
dying
me-
to say something,
No,
so
not
let
dying
him.
for that. I'm curious, maybe I'm missing something, but apparently you don't have any constraint on the volume.
No, this is a free boundary.
But even with a free boundary, you could have.
But they have very long fibers.
When you draw the
Because this is in
fiber,
back. There's
Yeah,
a-
it's
back.
extremely long.
Yeah.
And so,
There's a meniscus.
yeah, and this problem is really, I think there are many other things that can happen, but this problem was really, the energy and the situation of this constant cross-section and radial fibers was really motivated by this experiment and this idea of, could we see through energetically that these were stable, because they were, very long, very much R being constant, extremely small sizes, and extremely stable within a certain range of temperatures. Yeah.
So they are surrounded by a kind of melt.
Air. They pulled these in air.
Yeah.
I think it's just surface
Yeah,
tension that's
yeah.
There should be a kind of influx then of material to make them.
Yes, yes.
Oh, yes, at the ends, yes.
and
But
you
they
have
just-
pictures, just show the.
Yes, the pictures at the beginning,
Oh.
It means a mass
It
inserted
means that
in the
it's-
cross-section.
The cross-section is free.
Yeah.
they're they are extremely stable when they're done pulling them. And yes, there's volume that's gathering here.
But you have the diameters now there, it's the order of tens of microns, from 2 microns to 20
Oh,
microns.
yeah, we do.
That's-
Yeah, I could have put more pictures and other data, but I guess I,
First question, so for a Neanderthal like myself, so the telephone instability, is it splitting of the core into two? That's what the, because yeah, but I'm talking about the structure of the core, because from pneumatics, this is a two-dimensional problem which you translate. What happens, you always get core, singularity, one split into two halves. Which do you expect anything like this here, so that you, instead of one thing,
No,
you...
it's
It's
a difference.
Yeah.
Matrix you have +1 and -1 defect because you're polar. It's not. There are there are not.
But
Yeah.
I don't see why not, because if I take this picture, like you have just little two annular domain with smectic layers, why cannot I
Because your arrows, your directors, your molecule have got arrowheads on them, so you can't do halves.
Because the vector P is a vector.
It's true. Yeah.
yeah.
Well, but it depends on how exactly it orients, right? In certain orientations, it can accommodate for that, no?
No.
It
Not unless
doesn't.
your cone angle is like pi over 2 or something, which is the degenerate
Yeah.
case. Not a symmetric. Good. Thank you very much. I'm sure there'll be more questions that pop up over coffee.
Yeah, I think the telephone cord would happen really up in the aspect ratio. I don't remember exactly what aspect ratios we were getting, but it
Yes.
was fairly long. I think.
And, you know, I mean, one could also look at a model that would allow that type of thing, but this one doesn't.
Complicated enough as it is.
Yeah, no, I mean, you know, one could look at that situation. Here you're looking near this critical size and fiber.
It's basically the getting the twist instead of splaying on the whole fiber. That the whole
Yeah.
fiber it rotates.
Yeah.
Okay, thanks very much.